Let us now quickly discuss another problem, which is of a cantilever beam subjected to a concentrated load at the free end. So we have right hand side support, which is fixed. The left end is subjected to load P. The cantilever is of width T and height H. So the first step to solve this problem would be to assign a convenient coordinate system. So right from the beginning, we can see that this is a plane stress problem simplified into a 2D elastic problem. So x1 is along the horizontal axis, x2 is along the vertical axis, and the origin is right at the centroid of our cross section at the free end. In this problem, we will assume the body force equal to zero. Now, just like the previous simply supported beam problem, one thing we should appreciate that the ratios T by H and H by L is very important. Why are they important? Because these are the ratios which tells us whether the beam theory is applicable or not, and when would be the best time to implement the theory of elasticity. The reason I'm discussing this problem over here is that in this problem, I will try to derive the stress function. In the case of simply supported beam, we had the stress function already given to us in the question. In this question, we are not given any stress function. So just to give a flavor that how can we derive the stress function, the type of engineering judgment which is required, the type of assumptions which will be needed. So those will be discussed in this problem. It is important to establish sign convention, and after that we stick to that sign convention. So we have tension in all the direction taken as positive, and we would have shear, which is causing counterclockwise rotation in the vertical direction, will be taken as positive. We have to implement the static equivalence, which means to say that the Saint-Venant principle have to be applied. Thus, at the point of application of the load, it is not possible to get the actual representation of the internal stresses and displacement. Theory of elasticity will be able to give us actual representation at some distance from the location where disturbance is happening. So we can begin by discussing the boundary conditions, and from the boundary conditions we will try to derive our stress function. So first of all, we have got these vertical sides. The free vertical side has got load P applied, and this load P would be assumed to be taken by the internal shear stress at the face of free end. So that's why from minus h by 2 to plus h by 2 integral limit, we can write sigma 1 to t time dx2 is equal to plus p. The reason we have used plus p is that this is agreeing with our sign convention. This is similar to what we did previously, so I think so it should be straightforward. The reason we can apply this boundary condition is because of the static equivalence, and that should be kept in mind. Similarly, at x1 equal to 0, we have sigma 1 times dx2 times t equal to 0. We can also have another boundary condition, which is the moment at the free end equal to 0. So sigma 1 times x2 times dx2 will be equal to 0. So that would be integrated from minus h by 2 to plus h by 2. So this one is the axial force at this free end, and this one is the moment at free end equal to 0. Similarly, we can have the displacement, the horizontal displacement u alpha at x 1 equal to L equal to 0 because of the free end, and that has been written over here. So now let us try to derive the stress function. We will come up with other boundary condition as we go forward. Using these above boundary condition, we can set out the framework for our stress function, and then after that we can apply the additional boundary conditions and get the constants. So according to these boundary condition, one thing is clear, that the stress sigma 1 1, which is the axial stress in x1 direction, is proportional to moment about m3, and that is the definition of a flexure moment. Sigma 1 1 is proportional to m3, as we can see over here. In order to find out m3, we have to multiply that with x2 times t dx2, and also the moment is proportional to x1. So as we go further from the free end, we will have a moment developing right at the free end where the load is applied. Moment is 0. The moment we are referring to is the flexure moment. So as we move away from the free end, the flexure moment will keep on increasing. So therefore, we can write the moment is proportional to x1. Thus, we can also write that sigma 1 1 is proportional to a function of x2. So sigma 1 1 would be proportional to moment, and that moment will be a function of x2, as we can see from here also, that sigma 1 1 times x2, which is in the vertical direction, will give us the flexure moment. So based on that, we can also write that sigma 1 1 is proportional to a function of x2, and we assume that the function of x2 is equal to eta double dash x2. Now, why have we used double dash? The reason will become clear later, but one thing to appreciate in this type of problem is that we have to use lots of assumptions. Really, these shouldn't be called as assumptions. They were used by different mechanicians. So all these functions which you just see have been worked out based on trial and error in such a way that they satisfy all the required equations, which means to say that we take a twice differential function of x2, or a second order differential equation in x2. So just like a separation of variable, we can write phi comma 2 2, which is equal to sigma 1 1 x1 x2. This is from the Airy stress function, is equal to x1 times a function of x2, which we have taken eta double dash x2. So as I said, we are trying to develop a stress function, and we are using engineering judgment, but with that we use a lot of assumptions to come up with a viable stress function, and we have got to that point of assuming an adequate term within the function by lots of trial and error procedures. So we get phi comma 2 2 equal to x1 eta double dash x2. So this is a partial differential equation getting differentiated twice with respect to x2. So we can integrate it twice, and we will get two functions of x1. As we know, in the case of partial differential integration, we get constants with respect to all the variables except the one with which we are integrating against. So we get x1 eta x2 plus x2 time psi of x1 plus zeta times x1. Now, once we find out our phi, we can then differentiate this phi twice with respect to x1, and we get x2 time psi double prime x1 plus zeta double prime x1. We can find out minus phi comma 1 2, and that comes out to be minus eta prime x2 minus psi prime x1. So this is equal to sigma 1 2 as per our Airy stress function. Now let us apply some boundary condition to determine these functions, and we know that sigma 2 2 at x1 and plus minus h by 2 would be equal to plus h by 2 psi prime x1 plus zeta double prime x1 equal to 0, and minus h by 2 psi double prime x1 plus zeta x1 zeta double prime x1 equal to 0. So this is a boundary condition. It says that at for any x1 and x2 minus h by 2 and plus h by 2 boundary, there is no applied traction, so therefore everything is taken as 0. So this tells us if the positive, for positive it's 0 and for negative it is 0, that means to say that psi double prime x1 is equal to 0, and zeta double prime x1 is also equal to 0. So these two equations can only be satisfied if these two functions are equal to 0, and that gives us the value of psi x1 equal to ax1 plus f, and zeta x1 equal to gx1 plus h. So plugging these values back in the phi equation, so we get phi equal to x1 times eta x2 plus x2 small bracket ax1 plus f plus small bracket gx1 plus h. Now this equation must satisfy the compatibility equation. The right hand side of the compatibility equation again is taken as 0 because the body force is 0. Inverted delta 4 phi must be equal to 0. So plugging the values, we get phi comma 111 equal to 0, phi 2 phi comma 11 and 22 equal to 0. So this is just taking partial differentiation of this function, and we have phi comma 222 which is equal to x1 eta 4 times x. X2 is equal to 0, so integrating it 4 times gives us eta x2 is equal to b times x2 cube plus c x2 square plus dx2 plus j. The beauty of separation of variable is that in the end we get very nice ordinary differential equations of any order. That helps us to solve the integrations and differentiations very easily. So once eta x2 is worked out, remembering that in this equation we had x1 eta x2 plus x2 times small bracket ax1 plus f plus small bracket gx1 plus h. So we have found everything except eta x2. We used compatibility equation to find out our eta x2. We can plug the values in the phi equation and we get bx1 x2 cube plus small bracket x1 x2 square plus dx1 x2 plus jx1, then plus small bracket ax1 x2 plus fx2, and then plus small bracket 6x1 plus h. So we can combine the terms having the same degrees of variables. So we'll get bx1 x2 cube plus cx1 x2 square, a plus d we can write as a constant e, combined constant, time x1 x2 plus j plus 6 we can write k time x1 plus fx2 and plus a constant h. But we have to keep one thing in mind, that in such sort of functions we might have any in any constant without having any variable. So whether we write that constant or we ignore it, it's up to us. The reason is that in the case of Airy stress functions, the stress function is getting differentiated all the time. So it doesn't matter whatever constant we put behind our stress function. In the end, that constant will be eliminated. Therefore, whether we put this constant or we ignore it, it's up to us. So now we have our stress function defined, and we are in a better position to um, write a boundary condition and get our constants. So first boundary condition, sigma 1, 2 at x1 and plus minus h by 2. So at the top and bottom, we have no shear. So that is one of the boundary condition. And using that, we get the value of E equal to minus 3b h by 2 whole square. So again, plugging value of E in our stress function and finding out our stresses, we see that sigma 2 2 come out to be 0, sigma 1 1 comes out to be 6b x1 x2, and sigma 1 2 comes out to be equal to 3b big bracket h by 2 whole square minus x2 square. So although we can see lots of constants appearing over here like b, k, and f's, they become irrelevant when we work out our stresses using AD stress. The only constant we need comes out to be b. We can find out the other unknown constants also by using additional boundary conditions for the fixed end or the free end. So we can easily find out these constants also. But they are not relevant because without finding them, we can get all the information about stresses. So the stresses have got only one constant, which is B, and this can be worked out using some additional boundary condition. So those boundary conditions are that at x1 equal to 0, which is at the free end, our sigma 1 1 is 0. The moment about this end is 0, sigma 1 1 times x2. And at this point, the shear is equal to P. So it's the same conditions which we have mentioned over here. We can rewrite these ones, and we see that sigma 1 1 is equal to 0. So that is knocked out because x1 at x1 equal to 0, the whole stress it becomes 0. The only integration which is valid is this one, sigma 1 2, which is equal to 3b h by 2 minus x2 square. So we can plug the values over here and we get b is equal to 2p by th cube. Plugging the value back in our stress functions, we can get stress functions. It would be informative to use a formula we derived in the mechanics of solids, one, the elementary course on strength of materials, and compare that with the stresses we are getting over here. So in the mechanics of solid, we had a cantilever beam, and we could find the moments and shear at any point which is at some distance from the origin. So for that, we have to introduce something called moment of inertia, BH cubed by 12, a very well-known formula. And we have to find out the first area moment. So that comes out to be T by 2, big bracket, H by 2 whole square minus X2 square. Now, there are two formulas. One is the flexure formula, which is stress is equal to my over I, or in our case, minus mx2 over I. That is equal to sigma 1 1. So in the current elasticity case, it is 6b times x1 x2. However, in the previous case, it was equal to minus mx2 over I. Sigma 1 2 was called as shear, and shear was equal to VQ over IT. In order to refresh the memory, I would refer the listeners to go to the playlist of Moss 1 and check the flexure and shear stress equations. So in this formula, V is the applied shear, Q is the first moment of area, I is the moment of inertia, and T is the thickness. We can also write B in terms of I, remembering that I is BH cubed by 12, and that gives us B equal to P by 6I. That B can be plugged into these values, and we can easily get an equation minus mx2 over I. So if we compare the elementary beam theory with the theory of elasticity, we find that the stress equations stay the same. And this is unlike the previous case of simply supported beam, where we had other terms also included. In in the current case, we have sigma 1 exactly equal to minus mx2 over I, and that is the same as the Euler-Bernoulli equation. And sigma 1 2 is again equal to this value p by 2I h by 2 whole square minus x2 square. So essentially, both the stresses got from Airy stress function agree with the engineer's beam theory. Now we can derive our displacements. We came up with a proposal for our displacements while discussing the stress formulation. And we said that 2 mu u1 equal to minus phi comma 1 plus omega psi 1 2, and 2 mu u2 is equal to minus phi comma 2 plus omega psi comma 1. This can be omega w, whatever we want to call it. And the Laplacian of psi should be 0, and psi comma 1 2 is equal to Laplacian of phi time this term, which is a 44. So this term in our case would be equal to 0. So psi 1 2 would be equal to Laplacian of phi. So plugging values in these equations, we get psi 1 2 equal to p by I x1 x2. Psi x1 x2 then comes out to be p by 4I x1 square x2 square plus function of x1 plus g of x2. So a function of x1 and a function of x2, remembering that this is actually a partial integration. Now another condition to satisfy is that the Laplacian of psi must be equal to 0. So taking the double derivative of this function, first of all with respect to x1, then with respect to x2, we get p by 2I x1 square plus x2 square plus f of double dash x1 plus g of double dash x2. Now in this equation, we can separate the two variables, and each variable will be equal to 0. So p by 2I x1 square will be combined with f double dash x1, that is one term, and another term would be x2 square plus g double dash x2. And each of these two variable must be equal to some constant. So f double dash x1 equal to minus px1 square by 2I plus a. We have called that constant a, and that constant would be subtracted from another constant in order to get 0. So this is the same thing we did in a previous case, and that will help us to get the function x1 and x2. And our function x1 comes out to be minus p by 24I x1 4 plus a by 2 x1 square plus c1 x plus a constant. And similarly, g of x2 will be equal to minus p by 24I x2 power 4 minus a by 2 x2 square plus c 2 x2 plus constant. Thus, our psi will be equal to p by 24I small bracket 6x1 square x2 square minus x1 power 4 minus x2 power 4 plus a by 2 small bracket x1 square minus x2 square plus c1 x1 plus c2 x2. So we can write our equation 2 mu u1 and 2 mu u2 in the form of a function in terms of x2 and x1, and then we have another bracket in terms of x1 x2, and the constants. The reason that we have separated it in this form is that we can call this last matrix of constant of rigid body displacements. This bracket is a rigid body rotation, and these are actually the displacements. So, as we can see, a certain displacement should have some strain producing displacement and some portion of non-strain producing displacement. So non-strain producing displacements are actually the rigid body motion. This proposal of ours give us the rigid body motions, and along with that the displacement causing strains. This is clearly a rigid body rotation, as we discussed, and we will discuss that in a minute, how this is a rigid body rotation. But this one is clearly a rigid body displacement. So if we have a body at a distance AB and we just move it, that will give us a simple displacement. And if we put it in our strain equation, we will always get zero from this sort of displacement. Similarly, this rotation will also gives us a zero strain because it is purely a rotation. So the way to see whether something is got a rigid body rotation or not is that it is a skew symmetric matrix. After drawing the two displacement equations in this form, we have to check whether the displacement at the fixed end satisfies the boundary conditions. So, first of all, we have to find out what our boundary conditions are. So, in the case of cantilever beam, ideally, we want that at the fixed end, all the longitudinal fibers should have 0x2 displacement, 0x1 displacement, and 0 rotation. So, in other words, if we assume that our a vertical fiber is made up of infinite small pieces, at the fixed end, these pieces should not neither move up or down, right or left, or these pieces should not rotate at the fixed end. But it comes out that this type of boundary condition is very restrictive and it is almost impossible to achieve. So we have to relax this boundary condition. And the way to relax this boundary condition, we have to find out some additional equations. In these two equations, we call these constants as beta. We call these constants as d1, d2. So these are the displacement constants. As we said, this is the rotation constant. And we have got this term which involves displacement. So essentially, we have three unknowns in these equations. One is d1, d2, and beta. But we have two equations. So in order to get another equation, we can derive a considering rotation of a element. So we call it omega 2 1 is equal to half u2 comma 1 minus u1 comma 2. So if we have got a box like this one, u2 comma 1 means partial u2 by partial u1. So this is u2 by u1, and u1 comma 2 is u1 by u2. In other words, this is a definition of rotation. So if our rotations are getting added with each other, then that's a shear strain. But if they are getting subtracted from each other, then that's a rotation. So in this case, we have this box just rotating about a certain point. Therefore, one of the rotation is getting subtracted from another rotation. So plugging the value of u21 and u12, we get 4 mu theta is equal to pw by ix2 square minus pw by ix1 square plus 2 beta. So that gives us the third equation, and from these three equations we can get our beta d1 and d2. Let us first check whether at x1 is equal to L, we are getting beta d1 and d2 equal to 0. So if we plug the value of u alpha for L and x2, we find out that we get terms which are not 0. So even if we make our beta and d's equal to 0, overall we will get some displacements. So that is one issue which has to be resolved. And that is the reason that I said earlier that this condition of satisfying uh, these three constant for the whole fixed end is very restrictive. So we will try to just satisfy it for the center line or for the neutral axis, and we will try to relax it for the other ends. So in other words, the other ends could move in u1 and in the x2 direction. They can move in x1 and in x2 direction and also have rotation, but only the center line will stay the same. Now, this problem doesn't crop up in the case of a simple beam theory, because if we make the dimension of h very small as compared to the length, then this issue won't be a problem. But if this is a very big plate, or if our depth is of significant magnitude as compared to the length, then this problem will require some further consideration. We can check whether at x1 is equal to L, we have zero rotation or not. And when we plug the value in this rotation equation, we will again get some value showing that beta does not vanish. So we need three additional equation for finding out the unknowns beta, d1 and d2. And the way to get the three equation is either by integration formulation or making the constants 0. In the case of integration formulation, we take the three equations, 2 mu u1, 2 mu u2, and the rotation equation, and we integrate that about x2, which is vertical, and make that integral equal to 0. So that is a bit tedious, and from there we can get beta d1 and d2. So that process is a bit tedious. Therefore, the second one, which is more straightforward and it gives us a nice values of beta d1 and d2, that is normally implemented. So we can put our x2 equal to 0, which means that we just say that the neutral axis has to have beta d1 and d2 equal to 0, and the other fibers above the neutral axis at the fixed end can rotate. So if we put the values in the theta equation, which is this one, making x2 equal to 0, we get beta equal to pwl square by 2I. Similarly, in u1, if we plug values, we get d1 equal to 0 and d2 equal to wpl cube by 3I minus ph square l by 8I. So essentially, what we have said is that our neutral axis does not move up and down, and a small piece which is perpendicular to our neutral axis, that doesn't rotate. So we can plug the values in u2 equation, and we find that at x2 equal to 0 and x1 equal to 0, which is the free end, we would have wpl cube by 6 mu I plus ph square l by 16 mu I. So from here, we can get PL cube by 6 mu I, small bracket, W plus 3 by 8, small bracket, H by L whole square. So in this case, we have the free end having a vertical deflection, and there is another factor which is getting added to it, which is due to the shear deformation. Now, it is interesting to see that the second factor, which is related to shear, that will become negligible if our depth to span is very small. So if this is less than 1, then this term will almost become 0, and we will get the same answer which we get from our elementary formula. But if the depth is of significant proportion to length, then we will have a shear deformation, and which makes sense. The deep beams and walls, they are susceptible to shear. So theory of elasticity has given us information about both flexure and the shear contribution in the deflections, which elementary beam theory couldn't give us. Another important thing to appreciate is that the elementary beam theory is based on a plane section remaining plane. That means to say that if this straight section after bending will be exactly straight. However, because of our assumption that it is only the neutral axis which is perpendicular to our root and allowing the rotation and displacement of the other fibers, we have a scenario which looks something like this one. So the plane section doesn't actually remain plane in our theory of elasticity. So that means to say that the plane section with the neutral axis doesn't make a perpendicular angle. So we can see that this section is perpendicular to our neutral axis. The engineer's beam theory assumes that plane section remain plane, and in addition to that, it will always stay perpendicular to the neutral axis. However, the theory of elasticity allows this plane section to become curved, and correspondingly, this section not remaining perpendicular to our neutral axis, as we can see over here. This is because of this assumption which we have made over here for satisfying beta D1 and D2. We couldn't make all these fibers staying plane because that was too restrictive. So we had to relax some of the condition and allow the fibers above and below neutral axis at the root to have some deformation. Please note that we are considering this end as a fixed end. So this is at x1 is equal to L in our case.